So we have derived the reaction force, and this is the free body diagram, and we draw the shear force diagram for this beam, and this is shear force diagram from 0 to minus 13.5 kilonewton to 47.25 kilonewton, and across the beam this shear force equal to 0, and at the point B the shear force is negative 60.75 kilonewton. So the question is, what is the maximum positive bending moment? So we know the maximum bending moment is definitely happen at V equal to 0, because dm over dv over dx equal to V. Okay, if the shear force equal to 0, next mean this place have a maximum bending moment. Okay, so now we need to find the location where the shear force equal to 0. Okay, so how to find this location? So first of all, suppose we know the location is here. So we cut through this beam. We say A to A. We cut this beam A to A. So then we draw the free body diagram. So this is point A. Have a reaction force 60.5 kilonewton, and this is distributed node. And the distance here from here is x, and distance from free end to point A is 3 meters. So if we draw the coordinate system is y, x. So on this section we have shear force V and the bending moment M. Okay, so we need to find the expression for the shear force V. Okay, so we know the reaction force at point A 60.75 kilonewton, and we need to know the intensity of the distributed node at a location X. How to find intensity? So if we say this intensity is A, okay, so the intensity here is A. So look at here. So we want to know the intensity A here. So based on this geometry information, so we know A over 27 is equal to, we know the distance here is X over the whole distance from free end to B is 9 meters. Okay, so A, then we derive A equal to 3x. So we know the intensity here is 3x. So we know the value is 3x. So now we can derive the shear force. So we just write down the equation of equilibrium in vertical direction. So we assume the positive direction go up. So then for the point A, we have a reaction force 6.75 kilonewton, and the whole resultant force for this distributed node is showing here. So this is resultant force for this distributed node. So the resultant force is equal to the area of this distributed node. So the area is 3x times the free end to the cutting section is x, and over 2. So this is the area. So this is resultant force of this distributed node. So then it's going downward. So it's negative. So 3x times x is x squared over 2. So this is the resultant force, and we have the shear force is negative equal to 0. So the shear force V equal to 60.75 minus over 3x squared. So if we want to find the location of shear force equal to 0, then when equal to 0, then we can find the x. So based on this equation, we can derive x squared equal to, let's find 40.0. So x, then x equal to the approximately 6.36 meter. So this is the location that shear force equal to 0. Shear force equals 0. So then x equal to 6.36 meter. So after we know this location, then we can calculate the bending moment. So the bending moment, so we need to write down the moment equation of equilibrium. Suppose positive is going to clockwise equal to 0, and we know the reaction force and point A have the bending moment at this section A to A. So it's 60.75 times the distance is 6.36 minus 3. Okay, this is the distance from A to the section is 6.36 minus 3 meters. And then we got this one, then we negative, so we need to find the bending moment due to this resultant force, because this bending moment is going to counterclockwise, so it's negative. The value of this resultant force is equal to, so it is the area, so it's 3x squared over 2. This is the value of this resultant force. The distance from the resultant force point to the section is 1/3 of x. So times 1/3 of x. So 1/3 of x over 3. So this is the bending moment due to this resultant force, and minus m. M is going to counterclockwise equal to 0. We know x is equal to 0.36 meters. So x equal to 0.36 meters. Then based on these two equations, we can derive the bending moment of this section is equal to the result we can find after some calculation. We can find the result is equal to 75.5 kilonewton per meter. Okay, because at this location x equal to 6.36, the shear force equal to 0. So that means this bending moment is the maximum bending moment, and also this positive, so we say is maximum positive bending moment. Okay, that's it.